Welcome to this first lecture of the course Introduction to Electric Circuits. Before starting, what we have to do is to define what is an electric circuit. An electric circuit is an interconnection of electrical components. So basically, we move the definition of electric circuit to the definition of electric component. In order to define what is an electrical component, we have to go back to Maxwell's equations. Maxwell's equations define the relation between electric and magnetic fields. These fields are functions of space and time. So in general, we may say that all these fields are a function f of x, y, z, and t. In fact, what we see in the equations is that the curl operator and divergence operator appear, as well as the time derivative of the fields. Maxwell's equations can be used to study any electromagnetic phenomenon, so they can be used also to study electric circuits. But the use of Maxwell's equations is too complex. So the main hypothesis of electric circuit is that the dependence of the field variables with respect to space is solved at the beginning using the integration with respect to space, so that the physical variables have only time dependence. So in the end, we are going to study circuit using only field variables, in our case currents and voltages, that are only function of time. The fact that there is no dependence on space is usually referred to using the term lumped parameters. So that any spatial dependence of what we draw as a circuit and our variables is not taken into account. From our point of view, this means that if we have a specific object that we call electric component, in which we have electromagnetic phenomena that are developing inside this component. So inside here we have electric field, magnetic field, and all other dependent fields. The effect of these fields are not seen outside the component, but the only thing that we can see from the outside is that this component is talking, generally speaking, with the outside using the so-called terminals. So this is the electric component. The fields are developing only inside the boundary of the electric component, and the electric component can talk with the rest of the world through the terminals. In this specific course, we will study only two terminal components. And we will study only components that have linear behavior. So, in other words, the equations that rule in electric circuit are linear. Let me now introduce the physical quantities that we use to study electric circuit. The first one is the current. To define the current, we can define a piece of conductive material where an electric field is acting due to external sources. From physics, we know that if we have a free charge, let's call this charge Q, and this charge is immersed in an electric field, the charge starts moving. So, if we identify in this conductive material section and we count in this section the change of charges that flows through this section referred to the time interval, and we let this time interval goes to 0. So in other words, we take the time derivative of the charge. This quantity is called current. Or in a more precise way, we call this quantity electric current intensity. But in short, we say current. So if we refer to our generic component, and we said that we are going to study only two terminals component, like this one, the current is a physical quantity that flows through this component. And we say this by representing the current with an arrow that defines the direction of the current. And since we don't have any electrical phenomenon that is happening outside the component, the current that is flowing inside the two-terminal component is also flowing outside the electrical component itself. From a classification of physical theories, we can say that the current is a through quantity that is endowed by a direction. The current, of course, can be measured, and the units of the current are ampere. If we go back to the concept of the direction of the current, what we can say, for example, is that if for some reason we know that we have a component and we know the current that is flowing through this component, for example, the current that is flowing from the left to the right is 3 amps. What we can also say is that if we consider the current that is flowing with the opposite direction, so the current that is flowing from the right through the left, this current must be similar to the previous one, has the same magnitude, but it is opposite in sign. So the direction of the current is taken into account also with the sign of the number that is associated to the current itself. The current can be measured, and to measure a current we use a particular instrument that is called ammeter. The ammeter must see the same current that is flowing through the component. So if we want to see this current, we have to put here an instrument connected to the terminal of the component. This instrument is represented by a circle. We use the letter A to say that it is an ammeter. And since the current is endowed by a direction, we also have to know which direction of the current we are measuring. So, for this reason, what we have to do is to specify which is the terminal of the ammeter that is considered as a positive terminal, or in other words, if we identify the plus terminal of the ammeter, we may say that the ammeter is measuring the current that is flowing inside the plus terminal. So this device is measuring the current that is flowing from the left to the right. So if the reading of the ammeter is 3.5 amps, this means that the current is flowing from the left to the right and the value is 3.5 amps. If the reading is minus 3.5 amps, this means that we are measuring the current that is flowing from the left to the right, but actually the current is flowing from the right to the left. And this is represented by the sign of the reading of the instrument. The second quantity that we want to introduce is the voltage. Again, in order to introduce the voltage, we make reference to an electric field in a specific region of the space, and we also consider a charge Q that, because of the work made by the electric field, is moving from a point A to a point B. Of course, in order to move the charge from the point A to the point B, the electric field is using an external energy. And this external energy is called W. That is the energy required by the electric field to move the charge from the point A to the point B. Of course, the energy is measured in joules. We call the energy necessary to move the charge from A to B with W, AB. Now, if we measure the variation of energy from A to B with respect to the charge, and we let the charge approach 0, this quantity is the derivative of the energy with respect to the charge. And this quantity is called voltage. Note that from physics we know that the electric field is a conservative field. This means that if we move the charge using a different path, the energy required to move the charge from A to B along the red path is exactly the same energy required to move the charge through the green path. So we may say that this energy is dependent only on the initial and final point. For this reason, we can introduce a quantity that is called electric potential. We call this potential phi. And we can say that the voltage applied from the point A and the point B equals phi A, the potential of the point A, minus the potential of point B. So we may see the electric voltage also as an electric potential difference. And this quantity is also called sometimes as electromotive force. So, if we refer again to our basic electric component, with two terminals, what we can say is that the electric voltage is a quantity that depends on the initial starting point, so depends on the terminals only. We call this VAB, and this quantity, as represented on this picture, is an across quantity, and also this one is endowed by a direction. This means that we can also define another voltage that is the potential difference between B and A, and this quantity, called VBA, is nothing but minus VAB. I have represented the voltage with an arrow, but another possible representation that is similar to the previous one is a representation that is using plus and minus signs, so that the correspondence between the two graphical representations is that the plus corresponds to the tip of the arrow, while the minus terminal corresponds to the tail of the arrow. So this voltage is voltage VAB. The first notation is a notation that is mostly used in Europe, while the second notation is the notation that is usually used in US. The voltage is measured in system units in volts. And of course, also the voltage can be measured. If we consider the general two-terminal component. And if we want to measure the voltage, what we have to do is to identify the potential of the left terminal and the potential of the right terminal, and take the difference of the two potentials. So the instrument to measure this voltage is represented again by a circle, must sense the two potentials, so needs to have two probes that sense the two potentials. And since the voltage is endowed by a direction, we also have to identify one terminal as the positive terminal, so that we know that this instrument is measuring the voltage with the tip of the arrow on the left. Another physical quantity associated to electric circuits and electric component is power. Power, as in other physical systems, is defined as the time derivative of the energy. But if we apply the chain rule for the calculation of this derivative, we may say that we derive the energy with respect to the charge and then the charge with respect to time. With this decomposition, we can identify that the first derivative is the voltage and the second derivative is the current. So, in electric circuit, the power is associated with a component is the product between the voltage and the current. Of course, since these quantities can be positive or negative, also the power associated to a component can be positive or negative. The power is measured using watt. Suppose now that we want to measure the power associated to a component. This component is connected to a circuit, so we have a voltage applied to its terminals and the current flowing through the component itself. If we want to measure the power, what we have to do is to measure at the same time the voltage and the current. So we need an instrument called wattmeter that has two terminals for the measurement of the current, and of course also in this case we have to identify the positive terminal for measuring the current, and two terminals to measure the voltage. And also in this case we need to identify one terminal as the positive terminal for the voltage. So, in this case, we have defined an instrument that has four terminals. Two terminals are related to the measurement of the voltage and two terminals are related to the measurement of the current. This instrument is called wattmeter. When we have defined the power, we made reference to the concept of energy. What we are trying to do now is to reverse the point of view, and so we may say that the energy associated with a component is the time integral of power. Of course, the integral is defined between two time instants. And so this energy is associated to the time interval in between the times T1 and T2. In other words, if we have the power profile associated with a component in time, and we identify two time instants, T1 and T2, the energy associated with this component in the time interval T1, T2 is the area under the curve of the power. So, the power is an instantaneous quantity, whereas the energy is a quantity that is associated to a time interval. In fact, if you look at your energy bills, they are related to a specific time interval. Usually they refer to a time interval of 2 months. When we have introduced power, we generally said that the power is associated with a component. But this is not correct. In fact, the power can be absorbed by a component or generated by a component. For this reason, what we have to do now is to introduce what is called the sign convention. Let's make reference to our generic two-terminal component. This component is characterized from the electric point of view by a current flowing through the component itself and the voltage applied to this component. But this is not the only possibility, because the current can have two possible directions as well as the voltage can have two possible directions. So, the total combinations of directions for the current and the voltage creates four possible cases. If we want, we can also characterize the voltage with the plus sign. These are the possible combinations, but we can see that actually these four combinations can be combined into two main groups. For example, if we look at the first component, this component has the current that is flowing inside the plus terminal for the voltage. And the same happens in the last component, because in the last component the current is flowing outside the top terminal, and so it is flowing inside the bottom terminal. And so if we refer to the combination of the directions of voltage and current, these two versions of the component are characterized by the same orientation of the combination voltage current. And we call this orientation the P orientation. While in the other two cases, we have the current that is flowing outside the plus terminal, because in the first case, the current is flowing inside the top terminal, so it is flowing outside the bottom terminal. And in the second case, the current is flowing directly out of the plus terminal. We call this combination of voltage and current A combination. Now, we give a definition of these two combinations. The P combination is called passive sign convention. The current flows inside the plus terminal. Or, if you want, the current flows inside the terminal pointed by the tip of the arrow. The convention A is called active sign convention. In this case, the current flows outside the plus terminal. This is only a convention for the two physical quantities, voltage and current, and their direction. If we want to make an analogy, this is the same than considering the vertical axis with the zero on the ground and pointing up, or the vertical axis with the zero on the ground but the direction pointing down. It's just a way to study the component with the association of the direction, voltage, and current. Now, according to this sign convention, let's make reference to power. The power associated to a component is always P equal to VI. But this power has different meanings according to the active or passive sign convention. If we study the component according to the passive sign convention, the power P equals VI is the power absorbed by the component. So we may add the subscript P abs. Whereas if we study the component according to the active sign convention, the power P equals VI is the power generated by the component. So let's study, for example, the same component in the same conditions with two different sign conventions. So, for example, in the first case, we study the component according to the passive sign convention, and we have the voltage directed from the bottom to the top terminals, and the reading of the instrument is minus 4 volts. In the second case, we studied the component according to the active sign convention, and in this case, the voltage is reversed and, of course, changes with the sign, and it is 4 volt. Now, let's calculate the power in the two cases. In the first case, the power is VI, so it is minus 4 times 3, that is minus 12 watts. In the second case, the power is 4 times 3, that is 12 watts. Of course, in the two cases, we have obtained powers with opposite signs. But in the first case, since we are using the passive sign convention, the power that we are calculating is the power absorbed by the component. In the second case, the power is the power generated by the component. So, even if we have changed the convention for studying the component, we have obtained the same information from this analysis, because in the first case, we say that the component is absorbing a negative power. So, from a practical point of view, the component is supplying power to the rest of the circuit because it is absorbing a negative power. In the second case, we obtain a positive power, but this time this power is the power generated by the component. So the component is generating a positive power. So again, this component is supplying power to the rest of the circuit. As usually happens in physics, the conventions that we are using for studying a component are not affecting the real behavior from the physical point of view of the component itself. So the information that we can get from this analysis is exactly the same. Before concluding this first lecture, what I want to do is to introduce a notation that we use in electric circuit. The lowercase letters, so V, I, P, are used for time-varying quantities. So V is actually V of t, I is I of t, P is P of t. So, for example, we can say that V of t is 3 sine of 4t volt. This quantity is time varying. If we use instead uppercase letters like V, I, or P, we consider quantities that are constant in time. For example, V equals 3 volts. I'm also introducing another terminology that distinguish between DC and AC. DC stands for direct current, and with this term we mean that not only the currents but also all the voltages in the circuit are constant. With AC we mean alternating currents, and with this term we mean that in the circuit the currents and the voltages are sinusoidal. And this concludes the first lecture.